This presentation is about PLDM modeling of OCP 3.0 NIC. My name is Yuval Ivkin. I'm Distinguished Architect in Mellanox Technologies.
Hi, and I'm Ben Wei. I'm a System Software Engineer at Facebook.
PLDM modeling is referenced in OCP NIC 3.0 specification, which defines support for PLDM for monitor and control protocol on OCP NIC 3.0 compliant platforms, and that requirement is defined as part of the spec. The MTF 2054 document defines PLDM data structures for modeling a NIC using PLDM for monitor and control spec, which is DSP 248 semantics. The purpose of having a document to define how to model a NIC using PLDM for monitor and control is to guide people how to use the semantics of PLDM for monitor and control in order to map resources into a unified modeling schema in order to guarantee interoperability in devices provided by different vendors. This slide shows the conceptual modeling of a NIC. The root element of the model is the terminus ID, noted at the top. Terminus ID is only used to reference the root of the database records. These records are called PDRs, and each and every square on this diagram is represented using a PDR. The first element is the NIC, which is the PCB level that includes the physical elements which are assembled on the PCB card. Those includes one or more network controllers and one or more connectors into which the pluggable module, which represents the active cables which are inserted into those connectors, are modeled as well. So in order to reflect the connectivity of a given network port within the network controller to a given connector on the NIC level, another method was needed, which is called logical association, as noted at the bottom of this slide in the two squares marked with logical association. Those methods are used to represent which cable is connected to which network port of the network controller. This represents the physical connectivity of the PCB layer, routing the traces of the network controller through the connector and through the pluggable module until they reach the given cable. When modeling a network controller, we can see that the controller itself, in addition to having the network ports, is modeled with multiple attributes. Those attributes represent the temperature of the network controller, the silicon temperature. There could be one or multiple temperature sensors. It can represent the network controller power consumption values, if possible to measure those in runtime. That's best. If not, then profiled values could be used instead, such that the value being reported through this sensor will represent the expected power consumption during the present time at which the query is performed. Health state is also being reported in order to reflect the overall operational state of the device, if everything is okay or not okay, pretty much integrating the worst of all conditions from the various sensors included in the network controller. For each and every network port, there are additional sensors which are representing the link speed in measurable network connectivity parameters like megabits per second or gigabits per second, and the logical connectivity state of the port, be it active or not active, up or down, etc. The cable on its own could have its own active elements. The cable is modeled using an element called Pluggable Module, which represents the unit that connects to the physical cable, which is inserted into the connector, which is part of the PCB. The Pluggable Module is also represented using multiple sensors, like the state of the Pluggable Module. It could be as well healthy or not healthy. The temperature, if it's an active cable having temperature sensor, then it needs to have temperature measurement of the electronics within the cable. And the power consumption, similar to the use case as explained earlier for the network controller. The Pluggable Module itself may have one or more cables going out from the Pluggable Module to the physical network outside. In terms of enumeration scheme, this P248 uses attributes called IDs to identify different elements in the schema which represents the structure of the NIC. A container ID is used to uniquely identify each element which is represented using a container PDR. Container PDR is a PDR which represents a hierarchy that includes multiple elements in it. For example, the NIC, which was shown earlier, includes the connectors as well as the network controller. Therefore, the container ID for the NIC will represent the PDR which defines that hierarchy. Instance ID is another attribute which is unique for each entity within the hierarchy. Therefore, instance ID for temperature sensors within the network controller are enumerated independently from the instance ID of sensors at the active cable module or at the NIC level. Handle ID is yet another unique ID for each PDR in a model, which is used to allow the management controller to directly point to that particular PDR when it wants to read that one. Sensor ID is a unique value for each sensor in the model. Therefore, the sensor ID of the temperature sensor at the NIC level is different and guaranteed to be unique from all the other temperature sensors used in this model. This P2054 provides well-defined enumeration method for all the schema components which are used in the model.
All right, thanks, Yuval. I'm Ben Wei. I'm a system software engineer working on OpenBMC at Facebook. So here I will discuss how OpenBMC today supports the PLDM NIC models that Yuval just mentioned. So on OpenBMC, the default NIC monitoring daemon NCSID on startup, you will discover PLDM capabilities of the device. So for example, in the screenshot I attached, we can see how on this particular device, NCSID determined 1, device supports PLDM over NCSI, and 2, it shows the PLDM type it supports as well as the version spec where it supports. So here we see supports type 2, type 0, type 4, type 5 with the respective version. Right. Next, please. So once BMC determine the device supports PLDM, you will proceed to do discovery. So by discovery, you will try to determine what the terminus ID is there on the device and read all the PDRs available. So once it reads the PDRs, then you will know, okay, what's the container ID, what's the instance ID, the handle ID, and sensors. And then it will build a hierarchical tree to link all these together. So then BMC will have a complete picture of the niche and its pluggable modules and the number of sensors available. So once this is done, BMC can start monitoring the sensors. It will get the sensor threshold, start monitoring sensor. Additionally, on the BMC side, we have a command line utility, PLDM-util, which enables user to manually issue these commands to check the device check the device hierarchy and number of sensors. All right, next, please. So here's one example. So for example, the discovery is done automatically, but if the user wants to manually see what's the discovery results, we can use the PLDM-util Ethernet 0. So here it shows, okay, so in this device, we have 3 numeric sensors, 2 state sensors, 2 PDI repository, 1 pluggable module. And additionally, you can manually get the PDI information. For example, in the second screenshot, we manually get the PDI repo where it shows BMC will get the PDI information and it will parse it and show you the output. Right? And then now more example on the next slide. Next, please. So for example, here, we can also get individual PDIs. So these are for more like debug purpose or also more like for information because all the monitoring is happening in the background, right? So OpenBMC will start monitoring its own, but this is more for user to manually check to ensure the device is behaving properly. So we can manually get the PDI information. So for example, here, we try to get PDI 0, and this PDI, and then this is numeric sensor, and then what's the sensor ID, and then some other data that it will decode for you. So next, please. So once all this is done, then we can also use the BMC sensor util. So once the sensor information is discovered, BMC will also get the sensor threshold information through PLDM. So then we don't really need to use the PLDM util to read this individually. OpenBMC also provides a sensor util. In this example, for example, sensor util niche, it discovered this this device has a few temperature sensors and also some state sensors, the port speed sensors, for example. And additionally, we provide additional options, sensor util thresh, which shows the current reading and also the threshold as advertised by niche. Okay, next, please.
We highly encourage you to support us in OpenBMC. Of course, all the source code are available. You can go to the directory pointed here in order to get the files. Supporting cards are already available, capable of doing PLDM for monitor and control in OCP NIC 3.0 form factor. And we highly encourage you to join and follow the definitions in DMTF DSP 2054 in order to assure interoperability of your designs or of platform using designs compliant with DSP 2054. System vendors are highly encouraged to use OpenBMC code to support DSP 2054 as well as the all other OCP NIC 3.0 specifications. At this time, I'd like to thank you for being with us.